We have completed in the previous lectures the Fermi Dirac distribution law, and now it is time for the application of this Fermi Dirac statistics. Actually, first of all, Sommerfeld made the use of this Fermi Dirac statistics and proposed the free electron theory of metals. So, the first and foremost application of Fermi Dirac statistics, we consider the calculations, the useful calculations made by Sommerfeld. And in this regard, the most important application of Fermi Dirac statistics based on Sommerfeld's free electron theory of metals is the calculation of electronic specific heat of metals. Okay. As I have told you earlier, that this is a long discussion, and so I have divided this lecture in three parts, and this is actually the third and the final part of this lecture, uh, where we will calculate actually the electronic specific heat of metals particularly. Okay. In fact, this calculation needs the concept of density of states and Fermi energy. And you have already learnt in the previous lecture regarding the concept of density of states and particularly the Fermi energy. Okay. So, using those results which we have already discussed in previous two lectures, now we will be able to discuss the electronic specific heat of metals. Okay. As the previous results will be required, so I have mentioned the important results which will be needed for the discussion of today's lecture here for your convenience. You can see the first result which we have obtained is for the number of quantum states in the energy range E and E plus dE, which is also called density of states, and we have already discussed this density of states in very detail in the previous lecture, and you have seen that this density of states is simply the number of quantum states in the energy range E and E plus dE, and it is denoted by the symbol G of EdE, and it is equal to C times e to the power half dE. Here C is a constant, and the value of this constant you can see is equal to what? This C I have mentioned here that this C is equal to this much, and you have seen this value in the previous lecture, that this C is 4 pi V by H cube times 2m to the power 3 by 2. Okay. The another important expression which we have obtained was for the total number of electrons in a metallic specimen, and this result was n equal to C times 2 by 3 EF to the power 3 by 2, where you know that this EF is Fermi energy, and the expression for this Fermi energy EF you have seen earlier is this much. This is h square over 2m 3n divided by 8 pi v whole to the power 2 by 3, and you can equivalently write this n by v is equal, which I have mentioned it here. You can see this is number of electrons per unit volume. Okay. M here stands for mass of electron, and V is the volume of the potential box or the specimen. Okay. So these are the three important results which we have discussed in the previous lecture, and we will need the use of these results in the present lecture. Okay. So now we will talk about the specific heat capacity of solids or particularly metals. Okay. Actually, in case of metals, the heat conduction takes place by two means. There are two means for the heat conduction in metals. The first one is the free electron, the oscillation of free electron and its interaction with the neighboring electron contributes to the heat conduction. And at the same time, there is also lattice vibration in a metallic specimen, and that is also responsible for the heat conduction in metals. And that's why you can say that a specific heat of metals is contributed by these two means. The first one is the free electron, and when the specific heat is contributed by the free electron of metals, that is called its electronic specific heat. Okay, and when you consider the specific heat contributed by the lattice vibration, that is called actually the lattice specific heat. Actually, this lattice specific heat of solids was successfully calculated by Debye. Before that, there was actually the classical theory which is valid only at high temperature. After that, Einstein proposed the theory of lattice heat capacity of solids, but that was only qualitatively correct, not the TQ law was valid in case of Einstein's theory. Actually, the correct theory or correct calculation of lattice specific heat of solids was calculated by Debye. And I have already discussed this Debye theory of specific heat capacity in my lecture in the playlist of heat and thermodynamics, okay, thermal physics. So if you want to go through the details of this lattice specific heat capacity, you can see my video on this subject in the playlist of thermal physics and thermodynamics. Okay. In this lecture, I will just mention that result, but not I have done each and every calculation, because this problem has been already dealt by me in thermal physics. Okay. As the specific heat of metals is contributed by two sources, that is by free electron and lattice vibration. So if your aim is to find the total specific heat of metals, definitely you have to sum up these two specific heats. So the total specific heat of metals is simply the sum of these two specific heat, that is electronic specific heat and lattice specific heat. But the prime problem of this lecture is the calculation of electronic specific heat of metals, which is actually the application of Fermi Dirac statistics. Okay, and we are actually studying Fermi Dirac statistics. So our prime aim is the calculation of electronic specific heat of metals. Okay. Now we will calculate this very important quantity step by step. So for your convenience, I am mentioning the steps which will be followed in this calculation. So in this regard, first of all, we will calculate the total energy of the electrons at absolute zero temperature. Okay, you know, in classical theory, the energy of any system at absolute zero temperature, that is at 0 Kelvin temperature, is simply zero. But as Fermi Dirac statistics is a quantum statistics, and in quantum mechanics you know that vibration does not completely stop even at 0 Kelvin temperature. So definitely the electron will possess energy even when the temperature will be 0 Kelvin. So let us try to find the total energy of electron at 0 Kelvin temperature when the metallic specimen is at absolute zero temperature. Okay, and that this can be easily calculated by the use of Fermi Dirac statistics. Okay, you have actually studied in the previous lecture while we have discussed the concept of Fermi energy, that in a metallic specimen at 0 Kelvin temperature there is a level which is called Fermi level or the Fermi energy level. actually this Fermi energy level, which is denoted by EF, you know that at 0 Kelvin temperature, all the energy states, all the quantum states below this Fermi level are completely occupied, and above this Fermi level all the quantum states or energy levels are empty. So no electron is found above the Fermi level at 0 Kelvin temperature. Okay, so the energy of the electron at 0 Kelvin temperature will vary from 0 to EF when the temperature is 0 Kelvin. Okay, so we can easily find what will be the energy of the electrons at 0 Kelvin temperature. You know that this G of E dE represents the number of quantum states for energy between E and E plus dE. Since dE is very small, so you can on average consider that that the energy of each electron in this energy range is equal to E. Okay, and this G of E dE is the number of quantum states, and you know in one quantum state there can be only one electron, because electron is a fermion, it obeys the Pauli exclusion principle. So if the number of quantum states is G of E dE and energy of each electron is E, so the total energy of those electrons distributed in these quantum states will be simply G of E dE times E. And when you will integrate this result between the limits 0 and EF, then you will get the total energy. I think you have understand. Okay. So at absolute 0 temperature, the total energy E naught, I have denoted this by the symbol E naught. This is given by integral from 0 to EF G of E dE times E. Okay. Have you understand or not? Definitely you have understand. Okay. Now we have to evaluate this integral, but before evaluating this integral, we will transform this G of E dE in a standard form by the use of the previous result. You have seen that I have mentioned in this equation A1, you can see here that this G of E dE is equal to this much, and N, which is the total number of electrons, this is equal to this much. So let us divide this equation A1 by A2. Okay, then we can express the value of G of E dE in terms of EF. So G of E dE divided by N, you can see this will be C e to the power half dE divided by C into 2 by 3 EF to the power 3 by 2. So here this C and C will cancel out, and your result is what? Your result is 3 by 2 e to the power half dE divided by EF to the power 3 by 2. And so you can say that this density of a state G of E dE is simply equal to 3 by 2 times N e to the power half dE divided by EF to the power 3 by 2. Now we will make the use of this value of density of a state G of E dE, which we have obtained in equation 2, in equation 1. Okay, so using this result, you can see that this E naught will be equal to 3 by 2 N divided by EF to the power 3 by 2. These are actually constant factors, so it has been taken outside of the integral. And integral 0 to EF e to the power 3 by 2 dE. This is a very simple integral. You can see that this integral will be simply EF to the power 5 by 2 divided by 5 by 2. So our result becomes E naught equal to 3 by 2 times N over EF to the power 3 by 2 times 2 by 5 EF to the power 3 by 2. Now this EF to the power 3 by 2 will cancel out, and your result will become E naught equal to 3 by 5. This 2 and this 2 will also cancel out, and this is 3 by 5 N times EF. Okay, so this is the total energy of the n electrons at 0 Kelvin temperature. Okay. So if you want to find the average energy per electron at 0 Kelvin temperature, what will be that result? That average value I have written here inside this angular bracket. Okay. And this will be simply equal to E naught divided by N. E naught is the total energy, N is the total number of electrons. So when you will divide E naught by N, you will get the average energy per electron at 0 Kelvin temperature. And that is simply equal to 3 by 5 times EF. You can see that at absolute 0 temperature, energy varies from 0 to EF. Okay. So there will be some electron whose energy will be 0. There are also some electrons whose energy is equal to EF. There are electrons whose energy lies between 0 and EF. So the average energy is less than this EF and greater than 0. And that value is 3 by 5 EF, that is 0.6 EF. Okay. So this is a very important result. This result is also very important for the objective questions. If in your examination objective questions are asked, such type of questions is frequently asked. Okay. So remember this result. At absolute 0 temperature, average energy per electron in a metal is 3 by 5 times of the Fermi energy. Okay. This is a most important result. Now our aim is to find the average energy per electron at any temperature T, which is greater than 0 Kelvin. Okay. You know that at any temperature T, this we have to take under account the Fermi Dirac distribution function, which is actually called occupation probability. It represents the electron which occupies the energy state E. So the average energy per electron at any temperature T will be simply given by 1 over n integral 0 to infinity g of E dE times f of E into E. Okay. Here f of E, you know, this is Fermi Dirac distribution function. And here limits run from 0 to infinity. This is a classical concept. I have already told you earlier that Sommerfeld theory is a semi-classical theory. Some of the aspects is purely classical, and most of the aspects are quantum mechanical. Okay. Here the infinite energy is the classical concept. As the temperature is not 0 Kelvin, so the electron will be also found above the Fermi level. Because at absolute 0 temperature, all occupied states are below the Fermi level. But when temperature is greater than 0 Kelvin, then the energy levels which are above the Fermi level are also occupied by the electrons. And that's why here we have considered the upper limit equal to infinity. Okay. Now we will substitute the value of this f of E. You know, you have already studied that this f of E is equal to 1 over 1 plus e to the power E minus EF by kT. So here in this equation 5, the value of f of E has been substituted. Okay. Now you know that this number n, which represents the total number of electrons, how it is found? It is found by this. You have learnt it in the first lecture on density of states, that n is equal to integral 0 to infinity g of E dE times f of E. And f of E is again 1 over 1 plus e to the power E minus EF by kT. So from this result you can obtain the value of n, which you have already obtained earlier. Okay. At 0 Kelvin temperature, the limit will be EF, but at a temperature greater than 0 Kelvin, its limit will be infinity. So when actually this equation 6, which represents the total number of electrons, is used in this equation 5, and you will integrate. You will get a very simple result. But I have not done the calculations here, and that is not needed for a student of physics. For examination point of view, you must remember it, because this integral will be a very tedious integral, very uncommon integral, and it will take a large time for the calculation, okay, for the solution. So I have directly written here the value of this integral, and you can see after solving these two equations simultaneously, the result obtained for the average energy per electron at any temperature T is like this. This is E equal to E naught times 1 plus 5 pi square by 12 times kT divided by EF to the power whole 2. I am again suggesting you have to remember it, okay. Now, as we have calculated the average energy per electron, now it is very easy to calculate the electronic specific heat. From the definition of electronic specific heat, you know that the specific heat at constant volume, which is denoted by the symbol Cv, is given by del E by del T. This is partial derivative of this energy with respect to the absolute temperature. Now we will substitute the value of this average energy E. You know this average value of E naught is a constant factor, so it is taken outside of the differential operator, and this is del T operated on 1 plus 5 pi square by 12 kT over EF to the power 2. And as you can see that differential of this 1 will be 0, and 5 pi square by 12 k square by EF square is a constant factor. So all these constant factors has been taken here, and the differential coefficient of T square will be 2T. Okay. Now this 2 and this 12, this will be 6, and your result is Cv equal to 5 over 6 pi square k square T divided by EF square times average value of E naught. This is the value of Cv. Okay. But we have already calculated the value of this average value of E naught. You can see we have already calculated this value. This is the average value of E naught defined in this equation 6. So now we will substitute this value of E naught here in this equation 8, and this is your value. Okay. So Cv now becomes 5 by 6 pi square k square T over EF square times 3 over 5 EF. Okay. Now this 5 and this 5 will cancel out. This 3 times 2 will be 6, and so, and this EF will be also cancel out from this, and after simplification we simply get Cv equal to pi square over 2 k square by EF into T. But here this k square has been written in a particular manner. This is k over EF by k. Okay. You know that this EF by k energy divided by Boltzmann constant has a dimension of temperature, and so this EF by k is termed as Fermi temperature. This is called Fermi temperature. Actually this Fermi temperature is a constant for a particular metal, but for different metal its value will be different, because you know for different metal this Fermi energy EF is different. Okay. So this electronic specific heat, which I have denoted by this symbol Cv, comes out to be pi square over 2 times kT over Tf. You can see that this Cv is actually directly proportional to T. Okay. Cv varies linearly with T. You can see. So when you will plot a graph of this electronic, this Cv is what? This is electronic specific heat. Remember, electronic specific heat, okay, at constant volume. So from this result, as Cv varies linearly with T, so when we will plot this Cv in against of T, we will get a straight line as I have shown in this figure. And you can see that when temperature tends to 0 Kelvin, this electronic specific heat also tends to 0. Okay. So in this way, we have calculated the expression or the value for the electronic specific heat capacity of metal. Okay. But as I have told you earlier, that metal has another type of specific heat too due to the lattice vibration, and that lattice heat is actually called lattice specific heat. And as I have told you earlier, that this lattice specific heat has been already discussed by me in my video on device theory of specific heat capacity in the playlist of thermal physics. So you should watch that video for the detailed calculation. I have mentioned it here because this is not the application of Fermi Dirac statistics directly. Okay. So according to device theory, when this lattice specific heat capacity is calculated, although I have written here also Cv, but this Cv does not mean electronic specific heat capacity. This is lattice specific heat capacity of metal. And when you will see or when you will watch my video, you will see that this lattice heat capacity of metals comes out to be 12 pi to the power 4 divided by 5 R. Here R is actually the universal gas constant. T over Td to the power 3. Here Td is called device temperature. Okay. But this result is not the general result obtained by device theory. This result is a special result. This result holds only when we talk about the smaller temperature, not higher temperature. Actually, at higher temperature, even by device theory, it is found that a specific heat of solids becomes constant, and that is equal to 3R. So this result represents the specific heat capacity of metals due to the vibration of lattice at lower temperature. And so particularly at lower temperature, when you will plot this Cv, which is lattice specific heat capacity in against of T, the curve will be like this. You can see. And this is the lower temperature range where you can see that this Cv is proportional to T cube. While electronic specific heat varies linearly with T, this lattice specific heat capacity varies non-linearly with T. This is also called device TQ law, and this is experimentally valid. Okay. So you can see that our metals has actually two types of specific heat, and so the total specific heat of metal is given by the sum of these two specific heats. So this again I have written Cv, but now this Cv represents the total specific heat capacity, and this can be written as AT plus BT cube. Actually A here stands for pi square K divided by 2Tf, as you have seen earlier, and B stands for 12 pi to the power 4R divided by 5 Td cube. Okay. So you can equivalently write that this Cv over T is equal to A plus Bt square. Okay. This equation is just equivalent to y equal to C plus mx, which represents a straight line. This is equation of a straight line in slope form. So when you will plot this Cv over T in against of T square, not T, mark this, in against of T square, okay, then you will get a straight line like this as shown in this figure. Here this intercept A on the Cv by T axis or y axis represents the constant A, and this B is simply the slope of this straight line. So actually when experimentally this curve is plotted, you can easily find the value of A and B. Okay, and finding the value of A and B, we can easily find what will be the Fermi temperature and the device temperature for the solids. So getting the value of the intercept of a straight line on y-axis and its slope, we can find the value of Tf and Td, which are Fermi temperature and the device temperature. Okay, so I hope you have understand how we can calculate the electronic specific heat capacity of metal by using the Fermi Dirac statistics. Okay, thank you very much.